As far as the object detection matrix is concerned, I think it's instructive to just see the binary classification as and represent it as, if you like, a diagram like this, where we have, if you like, the complete universe of events that actually can happen and detections that actually can happen. With this actually line kind of represents the separation between what we call condition negative from condition positive, and this line could be anywhere over here. I just draw it as a vertical line, and on one side obviously we have events that are the negative events, truly negative events. This is basically the true positives. Or effectively, the positive events are the ones that satisfy, if you like, the condition that is to be tested, and the negative events, they don't. So we can also plot a boundary here, which is represented by this circular kind of line that effectively separates the correct classifications that a classifier did from the incorrect ones. So obviously here, if we have a ground truth of positive, and we can say that within this boundary, this is the true positive events, 1, 2, 3, 4 events over here, and on the other side there will be the true negative events correspondingly. And the second, the other two regions, on this side we have a ground truth positive, but unfortunately the classifier did not classify this as a positive, so effectively it classified it as a negative and therefore made a mistake, which we called false negative. And the other also, on the other side also we have a negative event as a ground truth, but effectively the classifier told us that it was a positive, and therefore we have in this region outside of this classifier boundary all the false positive events. Now let's look at an interesting use case to understand what we call the probabilistic notion of binary classification. So let's look at a use case where we have, I'll just draw it over here in the on the side. So we have a device, it's actually called radar, and the job of the device is to transmit a waveform that it will aiming to detect incoming planes. Okay, and the ability of the radar to detect incoming planes is actually due to the fact that the specific waveforms have some really nice autocorrelation properties. It is impinging into incoming a plane, and when there is a plane in fact there, then the signal is going to be reflected and come back to the receiver, and we will call this reflected signal X. Okay, and if there is absolutely no plane, then obviously there should be some other return. Maybe the signal is transmitted some faraway mountain, or some other kind of obstacle, and then there may be sort of flying flocks of birds or whatever, and then there will be another much weaker, if you like, return that comes back into the receiver. And the job really of the receiver, the radar receiver, is to sound the alarm when the plane is coming in, or not if it doesn't, with a very high sort of performance, the metrics of which we will see in a moment, what manifests kind of a good performance. So if we are to draw probabilistically, to view this problem in a kind of a bit more probabilistic setting, we could actually draw a diagram of what we call the signal strength. I mean, we can actually sit there as a kind of a radar operator, monitoring, if you like, a computer screen, and actually draw what we actually see as returns. So if I have on this axis, I have this what is called the radar received signal strength, let's call it. I will be observing probably something that it will consist of two sort of possibilities. Sometimes I'm on a day with no planes are actually coming, I will be probably observing some kind of probability distribution like this. And on a day where indeed in instances where we actually see something coming, I will plot something like this to represent that kind of signal strength. And there is some kind of a rationale behind it, because obviously when planes are not really coming, the signal strength would actually be on the left of when they do, because the average signal strength I'm expecting to be much lower when they are not than when they are. So there must be some, I mean, there is some kind of thinking about it. And as a reminder of in binary classification, we have effectively have y as noting as a label y, which is obviously a binary random variable which takes the value of 1 if I will call it a plane is incoming, which is the so-called positive condition here, and 0 if plane is not coming. Okay, so that's basically our label, and we have now x and y, and in fact we can create, if you like, even a data set where values x and y pairs is actually observable over time, and then we our job is really to sort of design something that we will call the threshold. And that we will deal in a moment. But before we do, let's try to put some, let's see what this the y-axis will be called. I would like to call this y-axis p of x comma y, because effectively we have a multimodal distribution as signal strength, and this multimodal distribution has, if you like, two components. When a plane is not coming, we can actually call this component p of y is equal to 0, x, and when the plane is coming, we can call it like this, p of y is equal to 1, x. So that's kind of a joint distribution of x and y, and obviously we will not be able to distinguish them as distinct probability distributions, but only by observing two different conditions separately. Only then we can actually plot them. In reality, what's going to happen, we will be observing this kind of joint probability distribution, and that is basically what we will see on aggregate. And then our job really there, and as you can see before we go into the threshold kind of discussion, as you can see, these two distributions are not separable, in a sense that they are not really even, they are spilling over, so that the tail of this distribution spills over into the other and vice versa. So you would expect to see in this kind of region, in terms of if you are to sort of monitor what is happening and create, if you like, a data set, you would expect to see something like that. So you will expect to see a lot of, probability distributions, a lot of events that are kind of negative, and as soon as we start seeing some perhaps not like this. As soon as we start going towards this on the right, you would expect to see some more positive events, but also some negative events as well, but definitely more positive towards that. So there is this kind of region where we expect to see some a mixture, if you like, of both positive and negative events because of this kind of overlapped overlapping situation. Okay, so what is really the job of the designer here, the classification designer, is really to come up with a scalar quantity. Mind you, we're dealing with a scalar case here, so x is a scalar. It just indicates the received signal strength, which is like in watts or some other measurement. It doesn't really matter right now. So, but the job really of the designer is really to come up with some threshold. Okay, in that threshold, I will call this threshold x hat, and I'll just write it also xth. That's the threshold of signal strength, and above this kind of threshold, so below this threshold, I will be declaring that no plane is coming. And above this threshold, I'll be declaring exactly the opposite. The y hat is equal to 1. And that is going to be my classifier. So the job really is to, and type of binary classifications, how to design properly this kind of threshold x hat. Okay, and I think it's very useful to actually observe right now that, you know, the moment we have, if you like, a threshold, my x-axis over here has been sort of divided in two regions, R0 and R1. The moment I'm actually introducing a threshold, I'm splitting this x-axis into these two regions, where the R0 region is on the left of the threshold, and the R1 region is on the right of the threshold. So now that the threshold kind of divided this line into two regions, I can actually start writing down the probability of making a mistake. The probability of making a mistake is obviously a probability of y hat is different than y. And this probability has effectively two components. One component is for events that are on the left side of the threshold, an event which is in the region R0, and events which are on the right side of the threshold, which is in region R1. So effectively, the probability of making the mistake on the left side is the probability of y is equal to 1, given that y hat is equal to 0. And also the probability of the other side of y is equal to 0, given that y hat is equal to 1. So these are the two components of the mistake that I can actually make, which I can actually write this component as p of y is equal to 1, given that x belongs to region R0, plus the probability of y is equal to 0 when x is in the region R1. Okay, so that is the two components that I have, and in fact, if I look closely, I can start drawing these two components, where the probability of y is equal to 0, given that x is equal to R1, is definitely this tail over here. And as you can see, this is because this region, this x is limited by the tail of this distribution, and correspondingly, this guy over here is associated with this large tail over here, where x is limited by the by the region R0, but still under the probability of x is equal to 1 condition. Okay, so this tail, I will divide it into two subregions, subtails I will call them, not regions, tails. And this is one of them, and the other one is this guy over here. So the summation of these two, and why I divided them up, it will become kind of apparent in a moment. And now definitely we can actually write this sum as each of these kind of terms has the integral over the region R0 of this tail over here of p of y is equal to 1 comma x dx. And this guy over here, we can actually write it as the integral over the region R1 of p of y is equal to 0 comma x dx. And as we can actually see now, this tail over here, this area under this tail, is the total component, the probability of making a mistake due to the effectively the false negatives, in the sense that in terms of ground truth, there are going to be some positive events of planes coming in this kind of area over here, especially in this neighborhood of this kind of thresholds on the left side, but we have falsely categorize them as negatives. So these are the false negatives. And this region over here with this horizontal kind of lines, it's actually very easy to see that yes, also in this area of the threshold on the right hand side, there will be negative events that are possible, but we are always categorize them as positive, so this will be the false positive. And using these two false positives and false negatives, now we can actually start making now this association between the previous diagram and this diagram. And we can make some interesting conclusions just by visual inspection of this diagram. Take, for example, the case where we move the threshold line to the left, then out of the total false negative component which can be impacted, definitely this component under this curve, this area over here, is definitely going to be reduced in terms of false, is going to move from the false negative region into the false positive region. But this part of the false negative is actually going to be, it's going to be 0. Because the threshold now is going to be right here. So this region here from this region becomes this little region, and it's not really difficult to imagine that there is specifically a threshold that goes through this point over here, and this I will call it the x hat star, which seems to be offering, if you like, the best situation in this specific example, because effectively this whole region has been eliminated of false negatives, and as we said before, the total region here in these both of these tails, effectively by moving that threshold, got unaffected. Therefore, definitely we have achieved a threshold with this threshold, a situation where the false negatives are kind of minimized. So there is, if you like, the total probability of mistake is minimized because effectively we minimized the total area under both of these distributions that are associated with the total probability of mistake. And so by effectively going back to this diagram over here, we can now start understanding how this classifier boundary can actually change. It will actually change by varying the threshold. So by varying the threshold, we can actually move this boundary in this kind of space And I think it is definitely the threshold, as it was shown before, was actually able to vary the trade-off between false positives and false negatives. And in binary classification, generally in classifiers, we have actually defined two ratios that capture, if you like, this trade-off. The first ratio is called recall, and I'm going to mention it over here. Recall, also known as sensitivity. And it's the ratio between true positives divided by true positive plus false negative. And that's one area, and obviously you can see recall and sensitivity have to do with the condition positive, I will call it performance, and as you can, if you remember, the false negatives that are associated with the recall and sensitivity formula are associated with this tail over here. Okay, on the other side, there is, if you like, the what is called precision, which is given by the true positive divided by true positive plus false positive. And as you can see, it has a lot to do with this erroneous, these false positives are actually present, or equivalently with this area over here under this tail of the distribution. And there is another ratio of interest that we will call false positive rate. And this false positive rate has the equivalent on the left side of what recall was on the right side, which is effectively the true negatives divided by, the false positives, false positive rate, it is false positive divided by the false positive plus true negative. And this is the false positive rate. And we can also associate these two with a curve that we will call the receiver operating curve. And the receiver operating curve will actually be the curve that relates the false positive rate or false alarm probability with the recall And also we can make some kind of intuitive kind of conclusions with respect to the shape of this curve, the receiver operating curve. And the receiver operating curve definitely seems to be leading to better classifiers. The taller it goes, faster. As really the ideal point is that we can have a recall of 1.0. This is the 1.0 point over here, with zero false alarm probability or false positive rate. So that is definitely the ideal point that we can actually have, and this is a bit higher than what it should be, but I hope you get the point. This is the ideal situation, that it's impossible to design a classifier like this, but the higher you go and approach this kind of point, the better the classifier becomes. And you know, a very bad classifier would actually be this kind of a straight line where effectively you have the classifier where the false positive rate and the true positive rate are the same. That's obviously a very bad classifier. Even worse classifier is that when you have curves like this, which is kind of obviously these are a really bad situation for you to design something like this. And as you can see, the receiver operating curve is definitely going to, it actually can be plotted by varying the threshold based on this kind of previous discussion. every single point that we have in the curve corresponds effectively to a unique threshold that the classifier is operating with. And that's called also sometimes the operating point. So for each threshold you are getting, based on this earlier discussion, a false positive rate and a false negative rate, and then you can vary, as you vary the threshold, you can actually get this receiver operating curve to plot.